So the next talk is by Suresh Gutta from the American Geotechnical and Environmental Services Incorporated, and he'll speak about new Baltimore landslide evolution of instrumentation. And take it from here, Suresh. Thank you.
Thank you, Eitan. Thank you very much to Iris and Faith for this opportunity and be part of this excellent group of speakers. Today I'm going to talk about New Baltimore landslide remediation. Really not going to get into the investigation of remediation or the construction process. For this presentation, I'm going to be exclusively talking about only on the instrumentation part of it. By the way, this was one of the largest landslides in Turnpike system for over 75 years, and it was remediated early 2019, and now there is no more landslide. All right, for anybody that were not aware of this location, here is Pennsylvania Turnpike, and you know this is Allegheny Tunnel, and this is about 3 miles east of Allegheny Tunnel. So if you are going down east, you would be able to see it on your right-hand side around milepost 126 on Pennsylvania Turnpike, which is I-76. A little bit on the history side. Pennsylvania Turnpike originally was constructed along old railroad alignment between Pittsburgh and Harrisburg, and this 160-mile stretch was open to public in 1940. As many of you know, that PA Turnpike was the first national superhighway. So what happened was, during the construction, as they were following the railroad alignment, original alignment, that they had to widen the track area and had to excavate into what was an ancient landslide. And that basically resulted in a huge landslide at the time. This was one of the historic photos that were shared by Pennsylvania Turnpike. Just to get a sense of how big it is, you can see the size of the houses versus the size of the slide, and a big chunk of slope just came down. This was a picture of the landslide before remediation. You can see the size of it, and see the size of the semi. That would give you a sense of how huge it was. Again, this is just a schematic view of the landslide. You can see that this is the Turnpike alignment. The width of the landslide was about 800 feet, length 1,500. And it was essentially moving along a soft bedrock seam, which was bedding at about 16 degrees. And this was the existing PA Turnpike. Anytime you are dealing with a landslide investigation, you have to basically come up with a generalized geologic cross-section based on field observations, recon surveys, and geotechnical borings and additional instrumentation. But before we really get into the instrumentation, you have to have a good model on how the landslide is happening. So this was just to give you an idea on how the subsurface conditions were. As I said, this was the Turnpike alignment, the dash line, and you could see that everything was moving along a soft clay siltstone, which was about bedding at about 16 degrees. And the strike of this bedding was bedrock was about parallel to the alignment. And the reason why we had to even remediate this landslide was because Turnpike, as part of the total reconstruction, they had to widen it and into the landslide, which means we were going to reactivate an already pretty active landslide. So, as I said, we are not going to be talking about how the slide was investigated, but instead we'll be talking about how we monitored during the design phase. As part of the monitoring, survey is a very basic and the first tool that is typically used in any landslide monitoring. And then you get into the actual instrumentation that could involve various tools like extensometers, TDRs, inclinometers, piezometers, and all kinds of stuff. But the type of instrumentation and the amount of monitoring depends on the complexity of the problem, as well as the availability of time and the consequence of the failure. For example, if it was actually moving at a much faster rate and there is a huge consequence to the property as well as the human life, obviously you would not be wasting your time in prolonging the instrumentation process. You would be jumping on to how to remediate it. But in this particular case, the slide had been moving for over 75 years at a average of 10 to 12 inches per minute. Per year. So we had quite a bit of data to really develop, use in our instrumentation program. This might look really overwhelming, but all I really want you to look at is this is a plan view of the landslide. This is the Turnpike, and the dots that you are seeing here are the survey monuments, and the circles are the inclinometer locations. All right, the survey was done very much from the beginning of our investigation on more like a bi-monthly basis. The data that is shown here was really the data collected from October 2010 to 2014, about 4 years of data. This gives a pretty good sense of the rate of movement, and as you can see, it is generally a uniform rate until you really dig into the localized zones to see which area is moving at faster or slower rate, and which times of the year it is moving. So that actually gives you a lot of good information that that also helps in developing an actual instrumentation program. So early in the investigation, we have used TDR monitors. TDRs were originally developed by electrical engineers to really monitor the deformations in coaxial transmission lines. In principle, it is very simple. You run a coaxial cable in a 1-inch PVC pipe installed within a borehole that is all grouted. So, and basically you send an electromagnetic pulse into this cable, and the reflection time it takes is recorded. So anywhere you have a kink, basically the reflection time, the delay in the reflection time gets translated into the actual displacement at that particular location. So this is what you get out of this instrumentation. You can see that this was the initial data, and after a few months you get the data. After 2 months you had this green data points, and then after the last set of data you could see this blue line. And obviously this is the failure plane where you didn't have any displacement. The depth is plotted on the horizontal scale in this particular one. The nice thing about TDRs is this is a great tool, especially when you don't know exactly where the failure plane is. So in that case, you basically install this, and after 1 or 2 data points, you would be able to pinpoint exactly where the failure plane is located. And then the early 2000s, we started using traditional slope inclinometers. Melly already went through some of these in his presentation. It involves basically running a slope inclinometer probe through casing, which is like a 4 grooves spaced at 90 degrees apart. And the probe runs on 2 sets of wheels. And these the sensors within the probe involves like servo accelerometers or tilt meters that measure the angle with the vertical. So that gets translated into the moments. So this is what you really get. This is the depth, and this is the moment. You'd actually basically these are the different data points taken at different times. You could see the cumulative displacement, and also you can see exactly where the failure pair is. The only problem with the traditional inclinometers was that you had to go physically and take the data. And especially when you're talking about a landslide that is so big as in New Baltimore, you're talking about 2 hours of trekking up and 2 hours hiking down, which was not an easy task, especially if you're carrying a lot of instruments. So that's when the Turnpike invested into in-place inclinometers. In principle, they work exactly same as the traditional inclinometers, except these probes were installed at the locations that we want to get more information. So in this particular boring, we basically installed the sensors at 5 feet spacing. And the nice thing about this is they will be installed within the inclinometer casing, and the readings are continuously taken. So you get like a real-time monitoring, and they were connected to a cell phone modem that would allow you to really access the data whenever you want on your computer remotely. So this gives us exactly pretty similar information as traditional inclinometers. Just a quick point that you can see that the spring and early summer is when you get most of the moments, and in the fall and late fall and down. It's a basic reason being that obviously there is a lot more rainfall in spring that really kicks accelerates the landslide movements. The other tool that's a very important tool in landslide monitoring is piezometers. There are 2 types. One is just a standpipe piezometer that gives you the depth of the water table, but what we use is the vibrating wire piezometer, which will allow you to measure the change in the pore water pressures. And the nice thing about that is you could see the pore water pressures, the changes with time. So every fluctuation in the pressure could be related to the moment and the lag time within the slope inclinometer data. That really it gives you a sense of how the rainfall, pore water pressure, and the moment and the lag time are all interrelated. During the construction, we have used the total laser total station system, which Melly already explained, which is essentially just a regular survey total station system installed on the other side of the turnpike on a hill, mounted in a shed powered up by a solar panel, and it was shooting the lasers into prisms installed all over the slide area that basically continuously measure the movement of the slide. And similar to in-place inclinometers, you get the real-time data, so you get a sense of how the slide was moving as the construction was going on.
You can take 2 more minutes if you need. Sorry, Suresh, you can take 2 more minutes if you need.
Okay, sure. Thanks. The nice thing about, well, there are limitations, sorry, with this total station system was that the accuracy of the data depends on the distance, the temperature, humidity, fog, and all kinds of things. But the nice thing about it is if there was a significant rate of movement, this could really capture that and send you like an email message or an automatic text message to alert you, and that really helped us during the construction to control all the movements. Fortunately, none of the trigger levels were really kicked in, and that means everything went relatively smoothly. Unfortunately, we had very limited time, so I couldn't get into the actual details of the slide investigation. But I highly recommend you checking this article that was published in Geostrata magazine in October 2018. It's free to access, and my colleague Ala Hazarvish and myself put together this very detailed article that explains how we investigated and how it was constructed. Once again, thank you very much for the opportunity.
Thank you, Suresh. Are there any questions regarding Suresh's presentation from anyone?
Suresh, this is Jack Zubek. Can you hear me?
Hi. Yes, hi, John.
The slope's been remediated by now, is that correct?
Yes.
Okay, and how has the movement been arrested as much as you hoped?
Well, it was monitored even after the slope was all remediated, I think the first few months. And since then, nothing has been reported, and I wasn't even checking. But so far, there hasn't been any noticeable movements that we observed.
Thank you.
Any other questions? Suresh, I have a question then. In your slide showing the profiles of movement between different seasons, it appears like in the spring,
yes,
most of the shear occurs on the failure plane. But in the winter, it looks like there is relatively a lot of motion at the upper portion of the profile. Is that associated with thaw, or with what causes that difference, you think?
That's a pretty good question. What we tried to do was we collected the rainfall data, and we correlated the rainfall data with the piezometer data and the slope inclinometer data. And what happened, our theory has been that since the slide is really in the bedrock, and there were quite a few major tension cracks. They were really wide cracks. What happened is there is a significant lag time after the rainfall data for us to observe the increase in the pore water pressure, and then change in the or the rate of the increase in the rate of movement. But we were able to get a sequence of events happening that every time there was like a 2-3 weeks of a delay between the increase in the pore water pressure and the movement in the landslide. But the thing is, the rate of movement is not uniform throughout the slide, and we had to really delineate the slide into several zones based on these moments. and the amount of crack that it had. But in general, there was always a lag time between the actual rainfall, increase in pore water pressure, and the movement. But after the movement happened, you could see that after 2-3 weeks of movement, it again reaches some kind of equilibrium and the pore water pressure goes down. I hope that answers your question.
It does.
Hey, Ton, there's 2 questions in chat that I noticed. Can you get there?
Sure. So one question that I see is from Gary Van Bylen, and the question is, for a chain of in-place inclinometer, are the readings from lower units in the chain, such as those below the top of the rock, adversely affected by movement of inclinometer that are connected to and above the inclinometer below the top of the rock? Do you see the question, Suresh?
Unfortunately, I'm not seeing the questions.
So I can read it. Can you open the chart on your screen? Or Gary, do you want to ask the question?
I can give my 2 cents on that. And so basically, actually, for any inclinometer measurement, we want a stable base. Basically, we don't, because the inclinometer is measuring a relative deformation regarding to a reference point, which is usually the base. So we anchor the casing to a rock so that it will not rotate or tilt. So that the measurements will be based off that reference point. So the lower points in the rock will not be affected, per the question. But if, it's the intention of the question was to see whether if there is extensive, deformation at any point within the rock or any shearing, as I mentioned before, of course, these system has a limit due to the limitation of the casing itself. After a certain point, it shears. But, the usual and customary application is you anchor the casing into a firm strata so that you can base off your deformations to that particular depth.
Thank you, Meli.
Thank you, Meli. Just to follow up.
Suresh, I apologize. It's just we're going to be taken out of the breakout room in a bit. Before this happens, I want to thank again Dan Messmer, Melich Demirkan, and Suresh Gutta for great talks, and for all of you for attending and for asking good questions. And the next thing that should happen is that you will see a note that you are being taken out of the breakout room. And until this happens, Suresh, you can go on and answer the question or complete your sentence. I apologize for cutting you.
No, absolutely not. Thank you very much.